Hi students, we are in the Solutions chapter. So what is a solution? Before we talk about what solutions are, I have to remind you about mixtures. And we talked about what mixtures are in a past chapter, and we said that we have heterogeneous mixtures and homogeneous mixtures. And with heterogeneous mixtures, you had two or more parts, and you could definitely see the interface, which was the boundary between one substance and another substance. So it's where one substance ends and the other one begins. And the two substances kept their own characteristics, like oil and water. Each one would have their own density and their own flammability and their own electrical conductivity values. Whereas with a homogeneous mixture, you don't have the interface. What you have is you have a mixture of substances that has the same characteristics throughout the entire mixture. So if you take a sample at one part of the mixture and you take a sample at another part of the mixture, you'll have the same chemical characteristics like density or electrical conductivity or solubility, that type of thing. So the definition on this slide says a homogeneous mixture that contains small particles, so atoms, ions, or molecules. And a solution contains two parts. We've got the solvent and we have the solute. Now, the solvent is the substance that dissolves another substance, and the solute is the substance that is being dissolved. So if we take a look at the picture to the right, we can see that we are putting copper sulfate into water. So we have copper sulfate and water right there, and right now we can see an interface, but spontaneously the copper 2 sulfate will dissolve into the water and the ions will spread out and they'll form a homogeneous mixture. So you'll see that once we have the solution complete over there, you don't see an interface or a boundary between one substance and another substance. With your eyeballs, you cannot see where the water ends and the copper sulfate ions begin. So it's consistent throughout, and you would have the same chemical and physical properties in your solution. So, another definition that we have is that the solvent is the substance that's present in greater amount, and the solvent is the substance that's present in lesser amount. And we can use those definitions when we are unsure which is the solvent and the solute in situations like when we dissolve water and ethanol in each other. So ethanol is a clear colorless substance and water is a clear colorless substance, and they both dissolve each other. So the question is, who's the solvent and who's the solute there if they're both dissolving each other? And so then we go with the present in greater and lesser amount and something like that. Okay, so when we think about solutions, we tend to think of dissolving a solid in a liquid, and usually the liquid is water. So if we're dissolving table salt, sodium chloride in water, that will form a salt solution, or if you dissolve sugar in water, that'll form a sugar solution. And again, once the solution forms, you don't see where the sugar molecule ends and the water molecules begin. You have a consistent substance throughout and no interface. Also, solutions aren't always a solid dissolving in a liquid to form a solution. You can have solutions in many forms. So the first example here shows a solution with gases. So air is actually a solution. So we have a mixture of Nitrogen, oxygen, carbon dioxide, there's also argon there. So we have gases and gases. And this one in the middle right here, that's the most popular example of a solution where you have sodium chloride dissolved in water. And we can see here how we have all the water molecules in the background there. And then that picture points out the ions, the sodium ion and the chloride ion, because the water actually pulls these things apart. So when you put solid sodium chloride into water, the water will come along and pull the ions apart, and then the ions float around in the water. And again, you don't see an interface here. You don't see the boundary between the water molecules and the sodium and the chloride ions. There's no interface. The third example over here is that we have a liquid in a solid. So we have mercury and silver there, and that's an amalgam. And what we usually use that for is for dental fillings. So let's identify the solvents and the solutes in the following mixtures. So number one should be pretty easy for you. We have 2.9 grams of sodium chloride and we have 200 grams of water. So the question is, first, who is the solute? Who is being dissolved? And most of us would guess that our salt, sodium chloride, is the solute. It's the thing being dissolved. And the water is the solvent, because we're used to water dissolving things, so that kind of makes sense. Also, the water is the substance that's present in greater amount, and the salt is the substance that's present in lesser amount. Number two says we have 25 milliliters of ethanol. So that's our drinking alcohol, the alcohol that's in beer, in wine, in whiskey. It's also a biofuel. And we have 20 milliliters of water. So the question is here, who's the solute and who's the solvent? And these things, like I said before, ethanol and water, they dissolve in each other. So we're going to go with who is present in greater amount and who is present in lesser amount. And we can see that we're used to water being the solvent, but here it's present in lesser amount. So that means it's the what? It's the solute. And that means that ethanol is our solvent. And ethanol is often used as a solvent in chemistry, especially if you go on to organic chemistry. Now, number three says we've got iodine and octane, and we have 2 grams of iodine and 20 grams of octane. Octane is a nonpolar substance, so water is a polar substance, and we've learned that in other lectures. Octane is non-polar, and where we would hear of octane is usually at the gas station. Our gas has an octane rating on it, and octane is a substance that has 8 carbons on it, and that would make sense because oct, right? Anyways, so octane is present in greater amount, so that's the what? That's the solvent. And iodine is present in lesser amounts, so that's the solute. So we would say that iodine's being dissolved in octane. Now, water is sometimes called the universal solvent, and this is because it's so common. It's used in all of our biological systems, like blood and interstitial tissue, cytoplasm, the aqueous humor in your eyes, all of that stuff. And it's really good at dissolving things, and part of the reason is that it's polar, and this polarity is pretty big, and that makes us have hydrogen bonds. And so these little water molecules are really good at attracting things to themselves and dissolving things. So what they do when they encounter other polar molecules or ions, things with whole charges, is that they point their positive ends, so we can see that right here, towards the negative ions, and they point their negative ends towards the positive ions. So if we have a negative ion like chloride, what the waters will do is they will point their partially positive ends, the hydrogens, towards the negative ion. And what they'll do with a positive ion is they'll point their partially negative end, the oxygen, towards that. And that does a couple of things. What it does is it pulls the ions off of the crystal there. So if we're thinking about a solid dissolving in water, what the water molecules will do is they'll come upon this crystal and they'll help the ions get away from the crystal. So you can see that the oxygen right there of the water is pointing itself towards the positively charged sodium ion, and it's like yoink, and it pulls it off of the crystal right there, and a bunch of waters will surround it. And then the waters do the opposite with the chloride ions. They point their partially positive end toward the negatively charged ion there, and they go yoink, and they pull the chloride off and they surround it. So it's pulling apart this crystal, so it's dissolving it. And what the waters also do when they surround the ions is they keep the ions from getting back together and making the crystal again, and this is called solvation. Solvation, not salvation. That's what happens in church on Sundays. This is chemistry, so this is solvation. So solvation lessens the attraction of our solute ions for each other. And so it keeps those ions in the solution or floating around in the water. So water is really good at dissolving things. It's really good at forming solutions, and that's because it's highly polar and has those hydrogen bonding properties. Now, even though water is known as a universal solvent, it doesn't dissolve everything. So when we want a solution to form, we need the solute and the solvent molecules to be attracted to each other. If our solute and our solvent molecules are not attracted to each other, you get situations like the oil and water mixture here. So the oil and water mixture, that is definitely a heterogeneous mixture. You can see the interface right there where one substance ends and the other substance begins. And if you take a sample from here and a sample from here, they're going to have different physical and chemical properties. So we're not forming a homogeneous solution here, a homogeneous mixture, which is called a solution, because the solvent and solute molecules are not attracted to each other. So what we say is like dissolves like. So polar solvents are going to dissolve polar solutes. So water is a polar solvent. We know that it's polar because we've learned this. And I drew it on the other slide. So it's got a partially positive and a partially negative side. The other way we can indicate that is with our dipole moment. So water is going to be attracted to other polar molecules and to ions because ions have whole charges. So we have attraction there. Nonpolar substances will be attracted to other nonpolar substances. So nonpolar substances will dissolve nonpolar solutes. An example is hexane. Hexane has 6 carbons, and it is surrounded by a bunch of hydrogens. So we've got 14 hydrogens here. And we can see that we do not have any polar bonds in this molecule. We only have nonpolar bonds, so we can't have a polar molecule. Hexane is nonpolar. So nonpolar substances will dissolve other nonpolar substances, and another example we have there is iodine. So if we take a look at the iodine molecule, one iodine has the same electronegativity as the other iodine, so neither iodine is pulling the electrons towards itself more than the other, so we don't have any polarity there. Hexane is actually used a lot as a solvent, especially in organic chemistry, and it's used to dissolve nonpolar solutes. So if you guys go on to organic chemistry, you'll see hexane a whole lot more. So the point of this slide is like dissolves like. So polar solvents are going to dissolve polar solutes and ionic solutes, whereas nonpolar solvents are going to dissolve nonpolar solutes. So let's take a look at these molecules here. So we want to explain why each substance will or will not dissolve in water. So we're going to take a look first at ammonia. So we've got NH3. And in the picture, it's already drawn for you that it's polar. So the nitrogen has the partial negative and the hydrogen side of the molecule is partially positive. So this right here is polar. So if water is polar and ammonia is polar, will ammonia dissolve in water? Yes. So ammonia is soluble in water because both of them are polar and like dissolves like. Okay. The next one we have is methane. So we've got CH4 here. Do we see any polar bonds in methane? Well, there's 2 ways that we can think about it. You guys can pull up the electronegativity chart that we had in the previous chapters, and you would see that the electronegativity for carbon is 2.5 and the electronegativity value for hydrogen is 2.1. So the difference there is 0.4, and we said 0.4 still counts as nonpolar. So you have 4 nonpolar bonds and you have no other bonds in this molecule. So if you have a bunch of nonpolar bonds, can your molecule be polar? No, so this is nonpolar. So is that going to be soluble in water? No. So that is insoluble in water because it's nonpolar, and water is polar, and like dissolves like. Okay, let's look at HCl. So do we remember whether HCl is polar or not? So we've done this molecule a whole lot in this class, and what we have is a dipole moment that looks like that. So chlorine is an electronegative atom, and it hogs the electrons over towards itself. So this right here is polar. So is this going to dissolve in water? Yes, soluble in water. And when HCl dissolves in H2O, what we get is hydrochloric acid. And hydrochloric acid definitely exists, and we use it quite often in the lab. So we know that HCl is definitely soluble in water. All right, so carbon tetrachloride, our next molecule over to the right. Now this might look like we have polarity somewhere because if we just look at each bond individually, say the carbon and chlorine, we might think, okay, yeah, it's polar because the chlorine is pulling the electrons out that way. But what we have is a chlorine pulling this way and a chlorine pulling this way and a chlorine pulling this way. So all of the chlorines on this molecule are equally pulling the electrons towards themselves, but when one pulls towards itself, the other pull back the other way and say, So what happens is, even though it looks like we have a bunch of polar bonds, in total, this is a non-polar molecule. So is this going to dissolve in water? No. So what we have to do with each substance is decide whether it's polar or not. So is it polar or ionic, or is it non-polar? So what we just did is we talked about whether something was soluble or insoluble in water. But solubility has varying degrees. So the definition of solubility is the amount of solute that will dissolve in a specific solvent under given conditions. So the solvent isn't always water. Like we said, sometimes we use hexane, sometimes we use ethanol, and different solutes will dissolve in different amounts in each of our different solvents. And also, different solutes will dissolve in different amounts at different temperatures or at different pressures or other conditions. Now, polar solutes will be more soluble in polar solvents. We already hit that point, as well as non-polar solutes will be more soluble in non-polar solvents. But we also have these sneaky little molecules that are called amphiphilic molecules. And amphiphilic molecules are molecules that have both hydrophobic and hydrophilic regions. So hydrophobic, that means water hating or afraid of water. So that's going to be our non-polar portions. And hydrophilic is water loving. So that's going to be our polar part. These molecules are soluble in both polar and non-polar solvents because if you put it in a polar solvent, the polar portion of the molecule will allow it to dissolve. And if you put it into a non-polar solvent, the non-polar portion of the molecule will allow it to dissolve. And the place that we see this most often is in biology when we're talking about the phospholipid bilayer. So when we think back to the phospholipid bilayer of a cell, what we have is we have these polar heads and they have non-polar tails. So we have the polar head here and we have non-polar tails. Now, the nonpolar tails are attracted to each other. So they aim themselves towards each other. So what the phospholipid bilayer will have is the little tails pointed towards each other. And let me switch to the red for the heads here. And they'll have the polar heads pointed into the cell to the cytoplasm. because the cytoplasm is made mostly of what? Of water. So if the cytoplasm is made mostly of water, then it's going to be polar inside the cell there. So you want to point your polar portion of your molecule towards the polar portion of the cell, the cytoplasm. And also you have fluids, interstitial fluids, and the intercellular fluid on the outside of the cell right here. So you also want to point your polar head out there. Now, the proteins and the oligosaccharides and all of that stuff, the transport proteins and on and on and on, I'll leave that to biology and chem to explain it to you. Okay, so solubility. When we want to talk about how soluble a solute is in a solvent, we're going to express it in grams of the solute per 100 grams of solvent. So say we want to express how soluble ethanol is in water, what we'll say is that you can dissolve 10 grams of ethanol in 100 grams of water. So that is the solubility of ethanol in water. And we're going to define our conditions, and here it says at 23 degrees Celsius. Now, if we have less than 10 grams of ethanol in our 100 grams of water, then the water can possibly dissolve more ethanol, so that would be an unsaturated solution. So a solution in which the solvent can possibly dissolve more solute. Now, if we've got 10 grams of ethanol in our 100 grams of water, that's going to be a saturated solution. So that's a solution in which the solvent cannot dissolve any more solute. Now, ethanol is soluble in water, and you can get 10 grams of it into 100 grams of water. But if you have a different substance other than ethanol, this number right here will be different. So looking at the picture down here, what we see is we've got some substance, a solid substance here, that is dissolving into water, and in the unsaturated picture, you've got 5 grams already dissolved and you have 95 grams that have not dissolved yet. And in the saturated side, you have 91 grams of that substance have dissolved in your solvent and 9 grams still sitting there at the bottom of the beaker that is not going to dissolve. And so we know that the solution is now saturated because no more of that solid will dissolve up into the solution. So what we have is a situation called dynamic equilibrium. So what is going on there in that saturated solution? Well, once you get a saturated solution, if you have your solute still sitting there, it might look like nothing's happening and the water or the solvent is just like, oh my goodness, I can't take on anymore, and so I'm not going to. And we might think that there is just absolutely nothing else going to happen. But what we actually have is we have a little bit of our solid dissolving into the solution, but at the same rate, we also have our ions coming back to the crystal. So there's a little bit dissolving up into the solvent, but at the same rate, we have the solute going back into the original material. So it looks like nothing's happening, and nothing is happening in terms of increasing the concentration of the solute in the solvent. But this just shows us that we still have some naughty little ions jumping out into the solution, but we also have some jumping back onto the crystal there. Okay, so how do we get more of our solute into our solvent? Well, if you have a solid solute, what you can do is you can heat it. And if you have a solid solute in a liquid solvent, you'll see the solubility of your solid solute increase with the temperature. So we can see right here, if we have potassium nitrate, if we heat it up, we can get more and more of it into the solvent. So look right here, if we have a temperature of 10 degrees Celsius, we can get 20 grams of potassium nitrate into 100 grams of water at 20 degrees Celsius. But if we heat the mixture up to 50 degrees Celsius, what we'll find is we can get so much more potassium nitrate into that same amount of solvent. You can get 90 grams of potassium nitrate in 100 grams of water at 50 degrees Celsius. And that's pretty amazing, the difference in how much potassium nitrate you can get into that 100 grams of solvent just by changing the temperature. Now look at sodium chloride. Sodium chloride is not very exciting. You can heat it up a whole lot and you aren't going to get a whole lot more sodium chloride into that solvent. So yeah, potassium nitrate, pretty amazing there. Okay, so what that allows us to do using that property is create something called a supersaturated solution. So you go ahead and you put 100 grams of your solid solute into your solvent here, and we'll assume that it's water. And then we let it dissolve and we let it come to equilibrium, and it's saturated right there. And then we're going to heat it up. And if we heat it up, we'll see that the rest of the solute will dissolve into the solvent. So it's up in the solution. And at 50 degrees Celsius, the solution is now unsaturated because it could possibly take on some more of that solid solute. So what we can do is then cool it really slowly. So we're going to cool it back down to 25 degrees. Now, the solvent at 25 degrees is only allowed to hold 91 grams of the solute. But if we let it cool slowly, what we can do is we can leave it alone and hope that the solvent molecules don't notice that they're carrying too much of the solute molecules or ions at that temperature. And that's called supersaturated because they're not supposed to have that much solute up there. But supersaturated situations are pretty unstable. So all you'd have to do is come along and tap the beaker a little bit, and your solute will fall out. So you'll see a solid form. And that's pretty cool when you watch that. So if you guys want to YouTube that, there's a lot of YouTube videos out there that'll show you that when you tap it, all of a sudden a solid will form. And that goes back to regular old saturated there. Okay, so what do we do if we want to get more gas solute into a liquid solvent? So we just did solid solute, and we said that you heat it up and you can get more solid solute into your liquid solvent. So what about if you have a gas solute? So say we're thinking about oxygen being dissolved in water, and I'm not talking about oxygen bubbles, because if you have, say you have a fish tank and it's full of water and you have oxygen bubbles. We wouldn't have pure oxygen bubbles, we'd have air bubbles, but just for the sake of simplicity, let's say oxygen bubbles. What you could see is you could see the boundary where the oxygen molecules end and the water molecules begin. So that's actually heterogeneous there. So that's not what we're talking about. What we're talking about is the oxygen molecules themselves that are dissolved in the water. You can't see where the oxygen molecule ends and the water molecule begins. And those oxygen molecules are what fish are picking up with their gills, and that's how they breathe. They don't go around gulping bubbles. Okay, so we're talking about oxygen being the solute and water being the solvent. So how do we increase the concentration of oxygen in water or any kind of gas in a liquid? So it's going to be the opposite of trying to increase the concentration of a solid solute. As you can see from the graph, as you heat up this solution, a gas in a liquid, the solubility of the gas goes down. So as you heat it up, those oxygen molecules are going to want to find each other and take off as gas. So you're losing your solute molecules, so you're decreasing your concentration of your gas solute in your solvent. So the question is, how would we increase the concentration of a gas solute? Well, it's the opposite. You would cool it down. And you can see as you cool down your solution, you are increasing the concentration of your gas there. Now, this scientific fact is unfortunate when we consider global warming, because as our small lakes and streams heat up, the oxygen that is dissolved in the water takes off. And what that means is that our aquatic and our marine life suffocate because they can't find the oxygen that they need because it has taken off in the gas form because we've warmed it too much. So occasionally we get situations like this picture shows where we get a lot of fish dying, and it's not a good situation. It's kind of smelly. So like we said, to increase the solubility of a gas in a liquid, we can decrease the temperature and we can also increase the pressure. And this brings us to Henry's law. So Henry's law says the solubility of a gas in a liquid is directly proportional. So that means when one goes up, the other one also goes up to the pressure of the gas above the liquid. So if we were to think of, say, oxygen dissolved in water, and this is the water, what you'll also have is oxygen molecules floating around above the water, and that should make sense to you when you think of real life situations. So if we increase the pressure, what happens is you have your oxygen molecules interacting with the surface of your solution a whole lot more, and that makes it really easy for the water to go yoink, yoink, and grab those oxygen molecules and keep them in solution. So if we look at the graph over to the right, we can see as the pressure of that gas increases, so does the solubility. So we can decrease the temperature or we can increase the pressure. So we've talked about how polar and ionic solutes tend to be soluble in polar solvents such as water. And that's a general rule, but sometimes we'll find that ionic solutes or ionic substances aren't soluble in water. And it's really important that we are able to figure out whether something is soluble or insoluble. And the way that we can easily do a prediction for this is to use this handy dandy general solubility rule chart. So this doesn't have absolutely every solubility conclusion on it, but it gives us some general rules that will allow us to make predictions about different salts. And salts meaning a substance that has a cation and an anion. So what we can see here is that all nitrates are soluble. So it doesn't matter what cation you put with nitrate, it's going to be soluble. So you can have sodium nitrate, or you can have calcium nitrate, or anything else, and it's going to be soluble. So that's one of those things that we should just know, that all nitrates are soluble. So all acetates tend to be soluble too, as well as anything you pair with chloride, bromide, or iodide, except silver, lead, and mercury. Now the next one says carbonates and phosphates. So all carbonates and phosphates are insoluble, and we're talking about solubility in water here. Okay, so water is the default solvent. So anything you're pairing with carbonates or phosphates are going to be insoluble, so not able to dissolve in water, except for when you put them with sodium, potassium, or NH4+. Do you remember what NH4+ is? It's our polyatomic ion that's a cation. It's ammonium. All right, moving on to hydroxides. Most hydroxides are insoluble except for when you put them with sodium and potassium. Hydroxides of barium and calcium, they're slightly soluble. Sulfides tend to be insoluble except for when you put them with sodium, calcium, strontium, and barium. Oxides are insoluble except those of sodium, potassium, strontium, and barium. Now, sodium, potassium, and ammonium, all salts of sodium, potassium, and ammonium, I don't know why it came out like that, but it should be NH4+, are soluble, except for we have some kind of uncommon ones we don't see very often. So if you see sodium, potassium, or ammonium, or chloride, bromide, or iodide, you tend to think these things are going to be soluble. Okay, so the question at the top says, how do we know that sodium chloride is soluble? Well, most of us do some cooking at some point, and so we know that when we put water with salt, we have the salt dissolving in the water. And then the next part of the question says, what about potassium bromide, and what about silver chloride? Okay, so how do we tell whether those are soluble or not? Well, we use the solubility chart. So looking at potassium bromide, well, right here it says all chlorides, bromides, and iodides are soluble except when you pair them with silver, lead, or mercury. We're not. We're pairing it with potassium. So we'd probably guess that this one is soluble. Also, down here, it says if you put things with sodium, potassium, or ammonium, they're going to be soluble. So you have a soluble cation with a soluble anion, so definitely soluble in water there. All right, what about silver chloride? Well, right here it says all chlorides, bromides, and iodides are soluble except when you pair it with silver. Okay, so this one right here is insoluble. So silver chloride is one of those special ones that makes the chloride containing compound insoluble. So what does that look like? Well, when we put sodium chloride into water, The water is going to dissolve sodium chloride because it's soluble in water, and it is going to form a homogeneous mixture. And what we also call homogeneous mixtures is what? Solutions. We're in the solution chapter. And the same thing's going to happen with potassium bromide. So when you have solid potassium bromide and you throw it into water, it's soluble in water, so water will dissolve it and you will form that homogeneous mixture, also called a solution. And when you have a solution or a homogeneous mixture or a homogeneous mixture, you do not see an interface. You do not see the boundary between one substance and another substance. And that's what we see there with sodium chloride and potassium bromide. Now, silver chloride is insoluble in water. So water does not dissolve it. So what happens is you have two phases here. And what we can definitely see is we can see the boundary between one substance and another substance. We can see the interface there. Now, when we have a heterogeneous mixture, when we have something that's insoluble in something else, we don't always have this what looks like this solid layer at the bottom. Sometimes it'll be up at the top floating. It just depends on what you're putting in what, okay? And then sometimes what you'll see is you'll see blobs floating. So insoluble molecules or blobs of them floating around because they're the same density or a little less than whatever you're trying to dissolve it in. Okay, so let's do some problems here. So which of the following compounds is soluble in water and which is insoluble? So the first one we have is ammonium iodide. So we have NH4 and we have I. So what we would do is we'd go back to our chart and we would look for one of our ions. So the first one we come to is the iodide, and it says all chlorides, bromides, and iodides are soluble. So right now we would assume that ammonium iodide is soluble. And it says except silver, lead, and mercury. Well, we don't have silver, lead, or mercury here. For our cation, we have ammonium. And then if we go to the bottom of our solubility chart, we can see that ammonium is there. And it says all salts of sodium, potassium, and ammonium are soluble. So right here, our cation, it tends to make things soluble, and our anion tends to make things soluble. So a really good guess is that ammonium iodide would be soluble or insoluble in water. Soluble, yep. So our first one right here, that's definitely soluble in water. Now our second one is calcium carbonate. So if we were to draw the ions in this, what this would look like is calcium +2, or you can put 2+, and we have carbonate, which is -2. So if we split it up like that and we look back at our chart, just going down the chart, la 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 la, what we can see here is we've got carbonate, and it says all carbonates and phosphates are insoluble except when you pair it with potassium, sodium, or ammonium. Now we don't have sodium, potassium, or ammonium. We have calcium. And we don't see calcium on the list, so since carbonate is making it insoluble, what we're going to do is say, okay, this one is probably insoluble. Okay, number 2 says, which of the following is probably nickel hydroxide in water, and which is most likely sodium sulfate in water? Well, alrighty. this one right here looks a whole lot more interesting than this one right here, a clear colorless solution. So if we have something in the tube on the left, it's going to be something that's soluble. It's dissolved in that water right there, and it formed a homogeneous mixture, a solution, and there's no interface. So if we're looking at our two substances, nickel hydroxide and sodium sulfate, do we notice something that always causes the compound to be soluble? What you might notice is we've got sodium there. So if we go back to our chart, because we want to use our chart, what we see right here is that all salts of sodium, potassium, and ammonium are soluble, except for if you have some uncommon ones. So we're going to assume that the sulfate is not an uncommon one, and we're going to say that sodium sulfate is soluble in water. And again, if something's soluble in water, it's going to dissolve into the water, and it's going to form a solution. It's going to form a homogeneous mixture, meaning you don't see an interface. You don't see a boundary between one thing and another thing. So this one is probably our sodium sulfate. So you see a nice clear colorless solution. Now, with this substance right here, you can see that there's something insoluble in there. So when we looked at silver chloride, we saw the insoluble substance sitting on the bottom, and I said it doesn't always do that. Sometimes you get this globulous layer thing at the top, and sometimes you get these little floaties, but what you don't get is one of these clear solutions where you don't have an interface. So here you can see that there is something in this solution that is insoluble, and it looks like there's more of it at the top than there is at the bottom. So if we look, if we say, okay, this is probably nickel hydroxide, but let's check on the solubility chart. So we don't see nickel listed anywhere here. So we're going to look for the hydroxide portion, and that's right here. And that says all hydroxides are insoluble, except those of sodium and potassium. Hydroxides of barium and calcium are slightly soluble, but we don't have barium or calcium. We don't have sodium or potassium. We have nickel. So what we're going to assume is that our nickel hydroxide is insoluble. And in fact, that is nickel hydroxide in water right there. It is insoluble, and you can see it sitting in there. Okay, so number 3 says, is the carbon dioxide that's dissolved in your soda. So say you have a can of soda. What you have is carbon dioxide gas dissolved in your liquid soda. So that consists of water and sugar and caffeine and other stuff. It's a solution of it. Is that carbon dioxide going to be more or less soluble when you open the can? So you've got your can of soda, and you've got carbon dioxide gas dissolved in your liquid soda, and then you pop the top, and what is your carbon dioxide going to want to do? It's going to want to take off. It's going to want to form bubbles and come out the top, because all of a sudden you have decreased the what on the inside of this solution, on those gas molecules. You've decreased the pressure. So inside the can, when it's closed up, it's pressurized. And when you pop the top, all of a sudden those gas molecules have somewhere to go. So they turn into CO2 gas. And that's good for us because we like bubbles in our soda. So once all of that gas is taken off, then the soda becomes what? It becomes flat. And most of us go, ugh, this is nasty. And then occasionally there's those people who like flat soda. And they're probably the same people who don't like pumpkin pie. I don't know how they exist, but they're out there. Okay, anyways. Now, those of you who don't like pumpkin pie all of a sudden hate me, and those of you who like pumpkin pie are laughing. Anyways, I'm just joking, you guys. Okay, so which of the following salts will be soluble in water and which will be insoluble? KCl, potassium chloride. So we've got potassium ions and we have chloride ions. Those are both soluble. And how on earth did I know that? Because I used the chart. And also I've been teaching for over 20 years, so I just know these things. All right, so you have a chloride ion and you have a potassium ion, and both of those cause things to be soluble. So if you have a couple of ions that are causing things to be soluble, then this is going to be soluble. And we're assuming that our solvent is water unless otherwise noted, okay? So what's going to happen is if you put potassium chloride into water, it's soluble, so the water will dissolve it. It'll take it up into the solution, and you will have a homogeneous mixture, so it will look clear, not necessarily colorless, because our first example was copper sulfate, which was a blue but clear solution. Okay, so it will be clear, so you won't see blobs floating around, and you'll see no interface. So it's not a heterogeneous mixture, it's a homogeneous mixture, also called a solution. Okay, the next question is silver oxide. All right, so silver oxide, looking at the chart, I need to erase some of this stuff on the chart just because it's getting too messy. Wah! There we go. Okay. So we don't see silver listed on this side, but we do see oxide. It says all oxides are insoluble except for sodium, potassium, strontium, and barium. Okay, but we have silver oxide, and that's not listed there. So we're going to assume insoluble. Okay. So insoluble. So again, when you put this stuff into water, it is insoluble. It will not dissolve. So you will see it with your eyeballs sitting in the water. It'll be on the bottom, it'll be floating on the top, or you'll have blobs of it floating around in your solvent. So you won't have a clear solution. Okay. So number 3 is cadmium sulfide. So back to the chart. I don't see cadmium there, but I do see sulfide. And it says all sulfides are insoluble, except blah, 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 blah. That does not include cadmium. So we're going to go insoluble with this one. And then we have iron hydroxide, and that's iron 2 hydroxide. So back to the chart. I don't see iron on the chart, but I do see hydroxide. And all hydroxides are insoluble, except if you pair them with sodium and potassium. And we don't see iron on there, so we're going to assume that this one is insoluble. So insoluble. Okay, the next one, number 5, we've got sodium phosphate. Okay, there's an ion there that you should recognize right away. Sodium. When you put sodium with things, what does sodium tend to do? Makes it soluble. And on our chart, what it says is when you have sodium, all salts of sodium, potassium, and ammonium. Again, ammonium is NH4 plus, not N, and then a little tiny H. So all salts of sodium are soluble except for some really weird ones. So over here it says all carbonates and phosphates, and we're talking about phosphate for this problem, are insoluble except when you pair it with sodium, potassium, or ammonium, and we are pairing it with sodium. So that means we're soluble. So you put sodium phosphate into water, what's it going to look like if it's soluble? If the water dissolves it? Are you going to see a layer at the bottom? Are you going to see a layer at the top? Are you going to see blobs floating around? No, not unless you put way too much sodium phosphate in there and the water can't take any more of it and it's, but we're not talking about that. Okay, so just in case you didn't believe me, here's pictures of this stuff. So we can see when it's soluble, you get a clear solution there. You don't see insoluble things in your solution. You don't see insoluble stuff sitting at the bottom, floating at the top, or floating around in there. Now, looking at the ones that are insoluble, you can see the stuff in there. Iron hydroxide, that looks like after you eat at Taco Bell. Yeah, not pretty. And you can see these guys are insoluble too. Now, when I'm talking about how when something's soluble, you have a clear solution, but it's not necessarily colorless, the soluble substance that we first started with at the very beginning of this lecture is copper 2 sulfate. And this stuff is soluble. And what you can see is that it makes a blue solution. So it's not colorless, but it is clear. You don't see copper sulfate blobs floating around, or you don't see a layer of it at the top, and you don't see a layer of it at the bottom. This is just initially right here. So this is not the solution yet. Once it dissolves up into the water, then you have this solution over here. So we can see that there's no interface there. There's no boundary that we can see with our eyeballs between the copper sulfate ions and the water there. Okay, so that concludes this lecture, and we will continue on with concentrations in our next lecture. Okay, bye-bye.